Hello everyone, my name is Sahar Tahvili. I'm a senior data scientist at Ericsson. Previously, I worked as a researcher at RISE Research Institute of Sweden. Also, I got my PhD in software testing from Malmö University in 2018, and with a close collaboration between Bombardier Transportation, RISE, and also Malmö University. Today in this talk, I'm going to present two tools which have been designed for test optimization purposes for Bombardier Transportation, ESPRET and Sortes, and later I'm going to present the tools and the performance of the tools and how the tools can be used for test optimization purposes. For designing and evaluating the mentioned tools, we analyzed three ongoing testing projects at Bombardier Transportation, C30, BR490 project, and also Zephyro projects. So in total, the number of test cases and requirements that we are analyzed for these three mentioned testing projects are more than 10,000 requirements and test cases. The first tool called ESPRET is a Python-based tool which is designed and developed for execution time prediction of manual integration test cases. Execution time is a critical factor which can be used for different test optimization purposes such as test case selection, scheduling, minimization. And this tool is designed by analyzing BR490 and C30 projects at Bombardier. The tool is able to read test a specification written in natural language text, and the output of the tool is a maximum time which this test case is needed for execution. When we are talking about execution time, actually we are talking about two main things. First, maximum execution time, and secondly, actual execution time. Maximum execution time is the maximum time that is which each test case is needed and is allowed to take for execution, and the actual execution time is the real time that each test case or test activity takes for execution. Actual execution time is a system-dependent time. Several factors can impact the actual execution time, but maximum execution time can be considered as a deadline, and we need to estimate that time just because regardless of which system and test station we are running test cases, the maximum execution time will be fixed for all test cases. Actual execution time is a factor which should be less or equal than the maximum execution time. As I mentioned before, both tools are designed for manual integration test cases. So here I have one example, one test case example extracted from Doors database at Bombardier for BR490 project. As we can see in this figure, all test activities are described in natural text with action and expected reaction, and the tester needs to follow up the structure in this file. But there is some information in this test specification which can be used for extracting the maximum execution time. Let's look at it in the bigger picture. So as we can see here, some of the time information are specified in the test specification, like step 3 that this test activity should be performed in 10 seconds. Then in step 4, the test activity is just waiting 20 seconds before we go for step 5, which should be conducted in 5 seconds. So as we can see, for some test specifications, some test activities, we have this information. So extracting this information from test specification or requirement specifications can help us to estimate what is the maximum time for executing a test case. For this purpose, we use NLTK, is a toolkit in Python for parsing and analyzing different factors specified in a test specification. In this table, you can see what we saved and what we parsed after analyzing different test specifications. This figure shows a screenshot of the database behind ESPRET. So we saved the test case ID, test case name, and we just saved one verb and supportive argument for each test steps in a test specification. Then if we could find a time information in the test specification, we saved that time, and if we couldn't find it, then we assume a baseline time as a 3 seconds, which we got it from subject matter experts at Bombardier. So if we check this example one more time, you can see we have, for instance, three main verbs login, but the objective argument is different for these three. It's like login to system A, system B, and system C, and we can see the time is different as well. So it's very important to save the objective argument. It's not enough just with saving time, just because saving verb, just because different objective can impact on the time. And as we can see in line 11, we couldn't find, the tool couldn't find any time specified in the test specification, and that's why we took 3 seconds, which is baseline time value for this test step. For some of those test steps and test cases that we couldn't find, we use this baseline time value. As I said before, this value comes from subject matter experts at Bombardier Transportation. But the actual execution time is also predictable. If we have the maximum execution time for each test step and having just 3 actual execution time after execution for the test cases, we are able to predict the actual execution time for test cases as well, which can be used for different purposes. For test optimization purposes, for ranking test cases, for selecting a subset of test cases for execution, the maximum execution time is good enough. We don't need to check the system setup. We don't need to check what is the property of each system and what would be the real time that each test case will take for execution. We use just maximum execution time, but in case if someone is interested to know what is the actual execution time, by using simple regression analysis technique, we are able to predict that time as well. This figure shows the user interface of ESPRET, which is implemented in Python. As we can see, we can easily browse the test specification, insert the test specification to the tool, and by clicking on the estimate button, we are able to see what is the maximum execution time for this test case. This test example comes from C30 project. We designed the tool for BR490 project, but we tested on C30 project test cases, and we can see what is the maximum time that we need to run this test case. So in this example, this test case will take 1.5 hour for execution, and the total number of test steps for this test case is 219. So this information can be used, as I said before, for test case selection. If we have just, for instance, 8 hours for executing large number of test cases, then we can decide if this test case is a good test candidate for execution or not. Just because this one will take 1.5 hours, and maybe we can execute 10 other test cases in 1.5 hours instead of this one. Of course, other factors like requirement coverage, code coverage, dependencies between test cases should be considered as well, but execution time by itself is a critical criteria which should be considered, especially when we are working on the deadline. The tool is not limited just to the mentioned test cases. The approach is general. If the timing information is specified somewhere, the tool is able to parse and analyze the timing information by capturing one verb and supportive argument for each test step. And if the time issue is not described in the text, if somehow we are able to capture the time information for each test activity, we can have this time information in the database, and again we can use the tool. The second tool that I'm going to present called Sortis, which is a supportive tool for stochastic scheduling of manual integration test cases. Sortis is designed by using and considering a critical criteria for test optimization purposes, especially in integration testing level, which is the dependencies between test cases. Dependencies between test cases can be considered as a functional dependency between test cases. Assume we have test case A and B. They are functionally dependent if they are designed to test different part of function F, or they are testing the interactions between two different functions, F1 and F2. Why we need to take care about the dependencies between test cases? Just because by doing some analysis on the failed test cases, we realize that more than 50% of test cases are failed just because of the dependencies between test cases. In this figure, we show a dependency graph between test cases. The white node in the left side represents an independent test case, and all other test cases in the first and second lines are dependent test cases. If you take the last test case in the right side for execution, there is a risk for getting failure for this test case just because all other test cases behind that one should be executed first. So sorters is designed by considering the dependency as the most critical criteria between test cases, and of course other criteria like execution time that I presented before and requirement coverage between test cases. But finding the dependencies between test cases is a critical task, and we need to have more information rather than just test cases. For instance, we need to know what is the relationship between requirements and specification, what is the relationship between software modules, and somehow we need to open the testing platform, which we did for BR90 project at Bombardier. We opened TCMS platform, train control management system, and we detect how software modules are communicating with each other. As we can see in this example, module 1 sends an internal signal to module 4, which makes module 4 dependent on module 1. So all test cases and requirements which are designed for module 1 should be executed before all test cases and requirements which are designed for module 4. For BR490 project, we had this chance to find the traceability graph for all requirements and test cases and software modules, and we could detect the dependencies between test cases just following up the relationship between software modules and monitoring the communication between internal signals between each module. Knowing this information helps us to detect the dependency graph between first requirements and later test cases. So this figure shows how test cases and requirements are depending on each other and what is the relationship between them for more than 7,000 test cases designed for BR490 project at Bombardier in the integration testing level. The blue nodes here represent the requirements and the red nodes represent test cases, and we can see how the interdependency between test cases and requirements are complicated. It's almost impossible to find the first node here. Which test case should be executed first? What is the second plan? So using this information, Sorters is able to first detect the dependencies between test cases and is able also to measure the requirement coverage, which means how many requirements will be covered by executing each single test case. This figure shows a user interface of Sorters. So the red lines here represent dependent test cases, and we have requirement coverage and execution time using ESPRET, the previous tool that I presented before, and we have test case ID. So we have a priority list here based on the dependencies, requirement coverage, and of course execution time. So our proposed solution is to rank first all independent test cases which cover more requirement, and then we go for first dependent test case. Another thing that the tool is able to do is as soon as we get a pass answer for after execution for each test case, by clicking on the button in the result column, the test case will be completely removed from the scheduling. So that's why we call the tool stochastic scheduling, just because the scheduling will be changed each time based on the execution result. You can use this tool by using, for instance, just requirement coverage. You can rank the test cases here just by ranking requirement coverage column or execution time if there's no dependencies between test cases. But if you have the dependency and you want to satisfy all three different requirements, then you should follow up the proposed solution by Sorters, which ranks these cases first based on dependency between them, and later we check the requirement coverage, and of course we have a control on the execution time as well. Comparing the performance of sorters with the current execution process for BR490 project at Bombardier, we can present these results. The red lines shows the execution plan for Bombardier and the requirement coverage, how many requirements will be covered each time by following up the current execution scheduling at Bombardier, and the green lines represent requirement coverage covered by sorters. We've checked 3 different execution phase for BR490 project at Bombardier Transportation, and you can see x-axis here represent the number of test cases, and in the y we can see how many requirements is covered each time. So for as you can see obviously in this figure, by executing less test cases we covered more requirements compared to current execution time at Bombardier, just because first we, as I said before, first we take care about the dependency, later the most critical criteria for us after dependency is the requirement coverage. So somehow we rank test cases based on the requirement coverage as well. That's why we could reach more requirement coverage by executing less test cases at each testing cycle in BR490 project. However, we are able also to minimize the troubleshooting time. Just because we are taking care about of the dependencies between test cases, less test cases will be failed in each testing cycle. If we take care about the dependency, then we have more chance to get pass answer for test cases which are ranked for execution. And here again, the red line shows the troubleshooting time for each test case and for entire project in 3 different phases. And the green line shows the troubleshooting time by using sorters. We also compare the performance of sorters against another approach in a state of the art, which calls historical based execution. The red lines here, which means that the failed test case, the first test case should be executed first. So we also compare the performance of sorters against Bombardier and historical base execution, and we can see, if I'm going to summarize the results, around 40% of test failure can be avoided by using sorters, just because no test case will be failed based on dependency. Of course, there is other reasons for failure for test cases, like the system is not ready and other factors, but we just minimize the failure based on the dependency using sorters, and at the same time we are increasing the requirement coverage up to 9.6% by using sorters. Both the tools that I presented here are not limited just to Bombardier or to the mentioned projects, and they can be used easily in different testing projects if we have the problem, for instance, of dependency, if we are able to extract the requirement coverage by using natural language processing techniques, or execution time if the time is specified somewhere in the test specification or requirement specification. Both tools are able to detect the mentioned factors. So we have a plan to release the tools as open source tools in the future, and we publish some papers and we present our results in the different papers. And in all papers that you can see in this slide, we have at least one industrial case study conducted from Bombardier Transportation. So that's all for me. Thank you very much. And if you have any question, feel free to contact me by my email address specified here. Bye.